In this lesson, we're going to take a look at the law of conservation of momentum. It's just like every other conservation law that we've seen. On the conservation of mass, we said the amount of mass before and after a chemical reaction remains constant. The law of conservation of energy said that the amount of energy does not change. In both of those cases, we can have mass change forms or energy change forms, but the overall amount didn't change. Same with conservation of momentum. The total amount of momentum in a closed system will not change. If there's an outside force that does some work to change it, then okay, we can change the momentum. But in a closed, isolated system, the amount of momentum remains constant. And we write that mathematically like this, where we say m1, which is the mass of the first object, times v1 prime. That little apostrophe is read as a prime, so that tells me starting momentum of the first object plus starting momentum of the second object, right? And if there were 3 or 4 or 5 objects, we just keep adding them up, is equal to the final momentum, m1 v1, plus the final momentum, m2 v2 of these two objects. And so what we're actually dealing with from this equation is that the momentum of a system is conserved, and we have to be consistent with that. So we have to define our system, and once we know what our system is, we know that the momentum within that system never changes unless an outside force acts on our system. So the law of conservation of momentum tells me that the momentum before and after an interaction is constant as long as no outside forces or masses enter or exit the system. So let's just do an example problem. Let's say we have our 2 objects in our system, and this one has a mass of 5 kilograms, and it's moving in a positive direction at 4 meters per second. And I've got another cart that's also got a mass of 5 kilograms, and it's moving in that direction at 2 meters per second. What happens if these 2 objects collide and link together? Okay? So this is my before picture. Before, I have 2 objects that are moving, they have momentum, but they're separate. But since this one is going faster than that one, it'll catch up. And eventually, I'll have these 2 carts together. Their masses won't change. That one's still 5 kilograms. This one's still 5 kilograms. But now, they'll be moving off in that direction at some other speed. What will that speed be? Well, we might be able to guess it, but we can show mathematically what it is. So we can say 4 times 5, that's the momentum we have to start with, plus 5 times 2, that's the other momentum we have to start with, right? So this is the momentum of the system at the beginning, is equal to 5 plus 5, and I'm adding those up because that's the mass of my one object now, because those 2 things stuck together, times their one velocity. I could say 5v plus 5v, but it's going to get me the same thing. So 4 times 5 is 20, 20 plus 10 is 30, so I have 30 equals 10v. Divide by 10, divide by 10, and I get a velocity of 3 meters per second. Now that maybe isn't surprising that their velocity ends up in the middle because they had the same mass, and so the one slowed down a little, the other one sped up a little. But we can do this for any combination of things, and they don't have to even be going the same direction, right? We just have to remember that momentum is a vector. So let's look at one more scenario where I have this cart, 5 kilograms, moving this way at 4 meters per second, so just like before, but this time this other cart is only 3 kilograms, and it's moving this way at 2 meters per second. Okay? And again, I'm going to have these 2 carts hit and stick to each other. Okay? So my before picture is like this, my after picture is like this. These 2 carts hit and stick. I want to know how fast are they going now that they're stuck together, and which direction are they moving? Okay? We should be able to get a pretty good guess from direction just by going, oh, this one has more mass and more velocity, it's got more momentum, it's harder to stop. This one has less mass, less velocity, less momentum, so it's easier to stop. But this is 5, this is 3, and so I have 5 times 4 plus negative 2 times 3. Remember that negative is important, is equal to 5 plus 3 because the two masses are stuck together, and so they have one velocity now. So I have 20 minus 6 equals 8v, and that is 14 equals 8v. Divide by 8, divide by 8, and I get v is equal to 1.75 meters per second. And that is a positive 1.75, which tells me they are in fact moving off to the right. Now, one last example. We're going to have the two objects, instead of stick together, we'll have them bounce apart. Okay? And so, cart, 4 kilograms, 5 meters per second. Second cart, 2 kilograms, and let's say that it is at rest. So it's got no velocity. But afterwards, I'm going to have my first cart only moving at 3 meters per second. It's still got a mass of 4 kilograms. What I want to know is, what is the velocity of my other cart? And actually not 3 meters per second, we're going to say 1 meter per second. What's the velocity of my other cart? So what I can say is my momentum to start with is 5 times 4 plus 2 times 0, which has to equal my momentum at the end, which is 4 times 1 plus 2 times v. And this time I did not keep those two together because they didn't stick, they hit each other, but they didn't stick. So 5 times 4 is 20, plus 0 is equal to 4 plus 2 times v. And so now I can subtract my 4 from both sides and get 16 equals 2v, divide by 2, divide by 2, and I see that that second cart has a velocity of 8 meters per second. So it's moving quite a bit faster in that direction.